Hello everyone, welcome back. In this video, we will discuss the top 50 tricky core Java interview questions for both beginners and experienced professionals. This is a full 1-hour Java interview guide that covers frequently asked interview questions with detailed answers. Let's begin. First, can primitive data types be null? No, primitive data types cannot be null in Java. Primitive types such as int, long, double, boolean and char always hold a value. When declared as local variables, they must be initialized before use. When declared as fields, they receive default values like 0 or false. The concept of null applies only to reference types, which point to objects. Primitives do not reference objects, so assigning null to a primitive results in a compilation error. Interviewers often ask this question to see whether candidates understand the difference between value types and reference types. Confusion usually arises when developers work with wrapper classes. Wrapper objects can be null because they are references, while primitives cannot. This distinction is critical in APIs, database mappings, and frameworks where null values may represent missing data. A strong answer explains that primitives are designed for performance and simplicity, while reference types allow null to represent absence of an object. Understanding this difference helps prevent runtime errors and incorrect assumptions in Java programs. Next, why do collections use wrapper classes instead of primitives? Java collections store objects, not primitive values. The collections framework was designed around object-oriented principles. All elements stored in collections must be reference types so they can support polymorphism, generics, and uniform behavior. Primitive types are not objects, so they cannot be directly stored in collections. Wrapper classes exist to bridge this gap by converting primitive values into objects. Another important reason is generic type safety. Generics work only with reference types. Using wrapper classes allows collections to enforce compile time type checking. Wrapper classes also support null values. This is useful when representing optional or missing data, which primitives cannot represent. Interviewers often want candidates to mention performance trade-offs. Wrapper objects consume more memory and involve boxing overhead compared to primitives. A strong answer explains that collections favor flexibility and type safety over raw performance, and wrapper classes make this possible while still allowing primitives to be used indirectly. Next, what is autoboxing and unboxing? Autoboxing is the automatic conversion of a primitive value into its corresponding wrapper object. Unboxing is the reverse process, where a wrapper object is automatically converted into its primitive value. These features were introduced to simplify code and reduce verbosity when working with primitives and collections. For example, when you add a primitive value to a collection, Java automatically converts it into a wrapper object. When you retrieve it and assign it to a primitive variable, Java automatically extracts the value. Interviewers ask this question to test whether candidates understand that these conversions are not free. Autoboxing and unboxing introduce hidden object creation and method calls, which can impact performance in tight loops or high-throughput systems. A strong answer explains that autoboxing improves readability but should be used carefully in performance-sensitive code. Understanding this concept helps developers write cleaner code without unknowingly introducing inefficiencies. Next question. Can autoboxing or unboxing cause a null pointer exception? Yes, unboxing can cause a null pointer exception. This happens when Java attempts to convert a null wrapper object into a primitive value. Since primitives cannot be null, the runtime throws a null pointer exception. This is a common interview trap. Many developers assume autoboxing and unboxing are safe because they are automatic. They are not. For example, Retrieving a value from a collection that returns null and assigning it to a primitive variable will cause an exception at runtime. Autoboxing itself does not cause this issue because primitives always have a value. The risk exists only during unboxing. Interviewers expect candidates to recognize this scenario and explain how it can be avoided. A strong answer explains that developers should handle null values explicitly and avoid relying on unboxing when null is a valid possibility. This question tests awareness of subtle runtime risks in otherwise clean-looking code. Next, when is string buffer preferred over string? String buffer is preferred when frequent modifications to a string are required. String objects are immutable. Every modification creates a new object, which increases memory usage and garbage collection overhead. String buffer allows in-place modification, making it more efficient for scenarios involving repeated concatenation or updates. Another important factor is thread safety. String buffer is synchronized, which makes it safe to use in multi-threaded environments where multiple threads modify the same string. Interviewers often ask this question to see whether candidates understand performance and concurrency trade-offs. While string buffer provides safety, synchronization adds overhead. For single-threaded scenarios, a non-synchronized alternative is usually preferred. A strong answer explains that string buffer is useful when thread safety is required and string content changes frequently, while immutable strings are better for simplicity and safety when no modification is needed. Next question: are there scenarios where the string pool is not beneficial? Yes, there are scenarios where using the string pool is not beneficial and can even hurt performance. The string pool is designed to save memory by reusing immutable string objects. However, this benefit applies mainly when many identical string literals are reused. If an application creates a large number of unique or dynamically generated strings, pooling them provides little benefit. Each string still occupies memory, and managing them in the pool adds an overhead. Another scenario is when strings are short-lived. Temporary strings used only during processing do not benefit from pooling because they are discarded quickly. In such cases, pooling can increase memory retention unnecessarily. In high-throughput systems, excessive use of interned strings can also cause contention because the pool is a shared structure. This may lead to performance bottlenecks. Interviewers ask this question to check whether candidates understand that the string pool is an optimization, not a universal solution. A strong answer explains that string pooling should be used intentionally, mainly for constants and frequently reused values, not for every string created in an application. Next, why are strings immutable in Java? Strings in Java are immutable, meaning their value cannot be changed once created. The primary reason is security. Strings are commonly used to store sensitive data such as usernames, passwords, file paths, and network addresses. If strings were mutable, malicious code could change their values after creation. Another important reason is string pooling. Immutability allows multiple references to safely point to the same string object without risk of modification. Immutability also improves thread safety. Since string objects never change, they can be shared freely across threads without synchronization. Performance is another factor. Immutable strings enable caching of hash codes, which improves performance in collections like maps. Interviewers expect candidates to mention that immutability is a deliberate design choice, not a limitation. A strong answer explains that immutability enables safety, reuse, and efficiency, making string one of the most reliable classes in the Java ecosystem. Next, how does equals differ from equals in string comparison? The equals operator compares references, not content. It checks whether two variables point to the same object in memory. The equals method compares actual content of the string. It checks whether the sequence of characters is the same. This difference is a classic interview trap. Two strings with the same characters may return false with equals equals if they are different objects. String pooling can sometimes make equals equals return true for string literals, which confuses beginners. But this behavior should never be relied upon. In real applications, content comparison should always use equals. Using equals equals for string comparison can lead to unpredictable bugs. Interviewers ask this question to test understanding of memory, references, and object equality. A strong answer explains that equals equals checks identity, equals checks equality, and using equals is the correct way to compare string values. Next, what happens when a string is created using the new keyword? When a string is created using the new keyword, a new object is always created in heap memory. Even if the same string value already exists in the string pool, the new keyword forces creation of a separate object. This means the reference does not point to the pooled string. Instead, it points to a distinct object with the same content. As a result, comparing such a string with a pooled literal using equals equals will return false even though equals returns true. Interviewers often ask this to test whether candidates understand how memory allocation works for strings. Using new is generally discouraged unless there is a specific reason to avoid pooling. A strong answer explains that creating strings with new bypasses the string pool, increases memory usage, and should be avoided in favor of literals whenever possible. Next question: how does string immutability improve security? String immutability improves security by preventing modification of sensitive data after creation. Strings are widely used to store security-critical information such as passwords, database URLs, file paths, and configuration values. If strings were mutable, an attacker could change these values while they are being used by the system. Immutability eliminates this risk. Another security benefit comes from safe sharing. Because strings cannot change, multiple parts of the application can use the same string instance without worrying about tampering. Immutability also prevents accidental modification by developers. Once created, a string's value remains consistent throughout execution. Interviewers expect candidates to connect immutability to real-world security concerns, not just theory. A strong answer explains that immutability makes string a trustworthy data type for sensitive operations, contributing significantly to Java's security model. What happens internally when an object is created using the new keyword? When we create an object using the new keyword, Java performs a sequence of steps behind the scenes. First, Java checks whether the class is already loaded into memory. If the class is not loaded, the JVM loads the class and prepares it for object creation. Next, memory is allocated for the object in the heap. This memory holds all instance variables of the object. At this point, Java assigns default values such as 0 for numbers, false for Boolean values, and null for object references. After memory allocation, the constructor of the class is executed. The constructor initializes the object with actual values provided by the programmer. Finally, a reference to the created object is returned and stored in a reference variable. The reference variable is used to access the object. In interviews, beginners should clearly explain that new does not just create an object but also allocates memory and calls the constructor. This question checks whether the candidate understands the basic object creation lifecycle in Java. Next, can we create an object without using the new keyword? If yes, how? Yes, it is possible to create objects in Java without directly using the new keyword. One common way is using factory methods. In this approach, a method returns an object and the caller does not know how the object is created internally. Another way is object cloning. When an object is cloned, Java creates a new object by copying an existing one without calling the constructor. Objects can also be created during deserialization. When data is read from a file or network and converted back into an object, Java creates the object automatically. Reflection is another mechanism used by frameworks to create objects dynamically at runtime. In interviews, beginners are not expected to explain all internals. Mentioning 2 or 3 methods with a simple explanation is enough. This question checks awareness beyond basic syntax. Next, can a class exist without any variables or methods? Yes, a class can exist without any variables or methods, and such a class is valid in Java. Even an empty class represents a type. It can be used to create objects or to group related concepts logically. In real projects, empty classes are sometimes used as marker classes. They signal special behavior to frameworks or tools. An empty class can also hold annotations which provide configuration information at runtime. From an object-oriented point of view, a class is not only about data and behavior, but also about identity and structure. Interviewers ask this question to test whether candidates understand the conceptual role of a class. A simple and confident explanation is sufficient for beginner-level interviews. Next question: what is the difference between an object and an object reference? An object is the actual instance created in memory, while an object reference is a variable that points to that object. The object itself lives in heap memory and contains data. The reference variable usually lives in stack memory and stores the address of the object. Multiple reference variables can point to the same object. If one reference changes the object's data, the change is visible through other references. If a reference variable is set to null, it no longer points to the object. However, the object may still exist if another reference is pointing to it. Interviewers ask this question to ensure the candidate understands how Java handles memory and references. This concept is fundamental for avoiding bugs related to object sharing. Next question: does assigning null to a reference delete the object? No, assigning null to a reference does not delete the object. It only removes that reference to the object. An object is deleted only when it becomes unreachable, meaning no references point to it. Once an object is unreachable, it becomes eligible for garbage collection. However, garbage collection does not happen immediately. The JVM decides when to free memory. Setting a reference to null is sometimes done to make an object eligible for garbage collection earlier, but it does not guarantee immediate cleanup. Interviewers expect beginners to clearly explain the difference between reference removal and object deletion. This shows an understanding of Java memory management basics. Next, can a class have only static members? If yes, is it still object-oriented? Yes, a class can have only static members, and this is completely valid in Java. Static members belong to the class itself, not to individual objects. This means we can access them without creating an object of the class. Utility classes like math helpers or constants classes often contain only static methods and variables. However, from a strict object-oriented perspective, such a class does not fully follow OOP principles. Object-oriented programming is based on objects, state, and behavior. Static members do not belong to any object, so concepts like polymorphism and inheritance are limited. That said, Java is a practical language, not a purely object-oriented one. It allows static-only classes for performance, simplicity, and convenience. In interviews, beginners should clearly say that static-only classes are allowed and commonly used, but they are more procedural than object-oriented. This answer shows balanced understanding, which interviewers appreciate. Next, is encapsulation only about making variables private? No, encapsulation is not just about making variables private. Encapsulation means hiding internal details and exposing only what is necessary. Making variables private is one part of it, but not the complete concept. Encapsulation is achieved by controlling access to data using methods. These methods define how the data can be read or modified. This allows validation, security, and flexibility. For example, instead of allowing direct access to a variable, we provide a method that checks whether the input value is valid before assigning it. If a class simply makes fields private but exposes them freely without any control, it does not fully benefit from encapsulation. Interviewers ask this question to check whether candidates understand the purpose behind access modifiers, not just a syntax. A beginner-friendly answer should focus on data protection and controlled access. Next, if a class has private fields but public setters, is it truly encapsulated? Not necessarily. Having private fields with public setters does not automatically guarantee proper encapsulation. If setters simply assign values without validation, the internal state of the object can still be modified freely. In such cases, making fields private adds very little protection. True encapsulation means that setters should enforce rules and protect the object's state. For example, a setter can prevent invalid values such as negative numbers or null values. Encapsulation is about maintaining consistency and integrity of data, not just restricting access. In interviews, beginners should explain that private fields are the first step, but meaningful logic inside setters completes encapsulation. This answer demonstrates understanding of design intent, not just coding habits. Next question: why do we use getters and setters instead of making fields public? Getters and setters allow controlled access to class fields. If fields are public, anyone can change them directly, which can lead to invalid or inconsistent object states. This makes debugging difficult and breaks encapsulation. Using getters and setters allows validation, logging, and future changes without breaking existing code. For example, if a field's logic changes later, only the method needs to be updated. Getters and setters also help maintain backward compatibility. External code does not depend on the internal structure of the class. Next question: can fields be public and still maintain encapsulation? In most cases, public fields break encapsulation. Encapsulation relies on hiding internal data and exposing behavior through methods. Public fields allow unrestricted access, which removes control over how data is modified. However, there are rare cases where public fields are acceptable. For example, immutable objects with final fields can safely expose data because the state cannot change. Constants are another common example. Public static final fields are often used to represent fixed values. In interviews, beginners should clearly say that public fields usually violate encapsulation with a brief mention of rare exceptions. This balanced answer shows clarity and maturity in understanding object-oriented design. Next, what are anonymous classes and where are they used? An anonymous class is a class without a name that is created and used at the same time. It is typically used when we need a small one-time implementation of an interface or abstract class. Instead of creating a separate class file, we define the class inline where it is needed. Anonymous classes are commonly used in event handling, callbacks, and simple behavior customization. For example, when we want to override a single method temporarily, anonymous classes are useful. They help reduce code clutter when the implementation is short and not reused elsewhere. However, anonymous classes have limitations. They cannot have constructors, and they are harder to read if the logic becomes complex. In interviews, beginners should explain that anonymous classes are best for short-lived logic and should not be overused. A good answer clearly states what they are, why they exist, and when to use them without going too deep into syntax. Next, what is the difference between encapsulation and abstraction? Encapsulation and abstraction are both core object-oriented principles, but they solve different problems. Encapsulation is about hiding internal data and controlling access to it. It focuses on how data is protected inside a class. Abstraction is about hiding implementation details and showing only essential behavior. It focuses on what an object does, not how it does it. Encapsulation is achieved using access modifiers and methods. Abstraction is achieved using interfaces and abstract classes. A simple way to remember this is encapsulation protects data, abstraction simplifies usage. Interviewers often ask this question to see if candidates confuse these two concepts. A beginner-friendly answer should clearly explain the purpose of each, rather than just giving definitions. Next question. What problem does abstraction solve that encapsulation does not? Encapsulation protects internal data, but it does not simplify how a system is used. This is where abstraction helps. Abstraction hides complex implementation details and exposes only necessary operations. This allows users of a class to focus on usage, not internal logic. For example, when we use a list interface, we do not care how elements are stored internally. We only care about operations like add, remove, and get. Encapsulation alone cannot hide complexity across multiple implementations. Abstraction allows different implementations to follow the same contract. Interviewers ask this question to check whether candidates understand design-level thinking. A strong beginner answer explains that abstraction improves simplicity, flexibility, and maintainability. This shows awareness of real-world software design, not just syntax. Next, why do we need abstract classes when interfaces already exist? Abstract classes and interfaces serve different purposes, even though both support abstraction. Abstract classes can have instance variables, constructors, and method implementations. Interfaces cannot hold state. Abstract classes are useful when classes share common behavior and state. They help avoid code duplication. Interfaces are used to define contracts that multiple unrelated classes can implement. They support multiple inheritance. In interviews, beginners should say that abstract classes represent an is-a relationship with shared behavior, while interfaces represent a can-do capability. This answer shows understanding of when to choose which abstraction tool. Next question. Can an abstract class exist without any abstract methods? Yes, an abstract class can exist without any abstract methods. Declaring a class as abstract prevents it from being instantiated. This is useful when the class is meant to be used only as a base class. Such abstract classes often provide common functionality and structure for subclasses. Even without abstract methods, the abstract keyword enforces design intent. It clearly communicates that the class is incomplete or not meant to be used directly. Interviewers ask this question to test knowledge of Java rules and design thinking. A beginner-friendly answer should focus on design intention, not just syntax rules. This demonstrates clarity and confidence in object-oriented concepts. What happens when a return statement is executed inside a try or catch block? Does the finally block still execute? Here is the answer. Yes, the finally block still executes even if a return statement is executed inside the try or catch block. This is one of the most common trick questions in Java interviews. Many developers assume that once a return statement is hit, execution stops immediately. That is not true when a finally block is present. When a return statement is encountered inside a try or catch, the JVM first evaluates the return value and stores it temporarily. Before the method actually returns to the caller, the finally block is executed. This behavior ensures that cleanup code such as closing resources, releasing locks, or logging always runs regardless of how the method exits. However, there is an important edge case. If the finally block itself contains a return statement, it overrides the return value from the try or catch block. This is considered bad practice because it makes code confusing and error prone. In real interviews, senior candidates are expected to mention both behaviors. First, finally always executes even after return. Second, returning from finally overrides earlier returns and should be avoided. This question tests understanding of Java execution flow, not syntax. Next, is it possible to write a try block without a catch block? How does try finally work? Yes, it is completely valid in Java to write a try block without a catch block as long as a finally block is present. The purpose of try finally is not to handle exceptions but to guarantee execution of cleanup logic. The code inside finally executes whether an exception occurs or not. In this structure, if an exception occurs inside the try block, it is not handled locally. Instead, it propagates to the calling method after the finally block executes. This pattern is commonly used when resources must be released no matter what happens. For example, releasing locks, closing files, or restoring system state. Many developers incorrectly believe catch is mandatory. Interviewers ask this question to test understanding of exception propagation and resource safety. It is important to note that try finally should not be used to hide exceptions. The finally block should only contain cleanup logic and should never swallow exceptions silently. A strong interview answer explains that try finally ensures reliability and resource safety, even when exception handling is delegated to higher layers. Next, under what conditions does a finally block not execute? In almost all normal cases, a finally block executes. However, there are a few rare but important situations where it does not. The most common scenario is when the JVM terminates abruptly. For example, if the program calls a system-level exit operation, the JVM shuts down immediately and does not execute the finally block. Another case is when the JVM crashes due to a fatal error such as memory exhaustion or native level failure. In such cases, Java does not get a chance to execute finally. If a thread is forcibly stopped by the runtime, the finally block may also be skipped. This is one reason why forcefully stopping threads is discouraged. Interviewers ask this question to check whether the candidate understands that finally is reliable but not absolute. A good answer clearly states that finally executes in logical program flow, but not in situations where the JVM itself is terminated or crashes. This demonstrates maturity in understanding real runtime behavior, not just language rules. Next, can we write multiple finally blocks in Java? Why or why not? No, Java does not allow multiple finally blocks for a single try statement. Each try block can have either 0 or 1 finally block. Allowing multiple finally blocks would introduce ambiguity and complicate execution flow. The purpose of finally is to define a single guaranteed cleanup section. Having more than one would raise questions such as execution order and responsibility separation. If developers need multiple cleanup steps, they should be placed inside the same finally block in a clear and readable manner. Interviewers often ask this question to see whether candidates understand Java syntax rules and the design intent behind them. A strong answer explains not only that multiple finally blocks are not allowed, but also why Java enforces this restriction. Java prefers simplicity and predictability in exception handling. A single finally block ensures clear execution semantics and avoids unnecessary complexity. Next, how does exception handling impact the performance of a Java application? Exception handling itself does not significantly impact performance when exceptions are not thrown. However, throwing and catching exceptions is expensive. Creating exception objects, capturing stack traces, and unwinding the call stack consume CPU and memory. This is why exceptions should not be used for normal control flow. Using exceptions for logic decisions can severely degrade performance, especially in high-throughput systems. For example, using exceptions to handle common validation failures instead of conditional checks is a bad practice. In performance-critical systems, exceptions should represent truly exceptional situations, not expected outcomes. Interviewers expect candidates to mention that try-catch blocks themselves are cheap, but exception throwing is costly. A good answer also highlights that excessive logging inside catch blocks can further worsen performance. Understanding this distinction shows that the developer knows how to write efficient and robust Java applications. Next, how can you handle multiple exceptions in a single catch block? Java allows handling multiple exceptions in a single catch block using a single catch statement that lists multiple exception types separated by a logical OR. This feature was introduced to reduce code duplication when different exceptions require the same handling logic. Instead of writing multiple catch blocks with identical code, they can be combined into one. This approach improves readability and maintainability. If the handling logic needs to change, it is updated in one place instead of several. However, there is an important rule that interviewers often test. The exceptions listed in a single catch block must not have a parent-child relationship. If one exception is a subclass of another, the compiler will reject it. Inside a multi-catch block, the caught exception variable is implicitly final. This means it cannot be reassigned. This restriction prevents accidental modification of the exception reference. In real interviews, candidates are expected to explain not just the syntax, but when to use multi-catch. It should be used only when the recovery or handling logic is truly the same for all exceptions. Using multi-catch blindly can hide important differences between error scenarios, which is a common design mistake. Next, can a static block throw an exception? Yes, a static block can throw an exception, but this behavior has serious consequences. Static blocks execute when the class is loaded by the JVM. If an unchecked exception occurs in a static block, class initialization fails. As a result, the class becomes unusable for the rest of the program. Checked exceptions cannot be thrown directly from a static block unless they are wrapped inside an unchecked exception. This is because static blocks do not allow declaring throws clauses. If a static block fails, the JVM throws a special error indicating that class initialization failed. Any future attempt to use that class results in a failure. Interviewers ask this question to test understanding of class loading and initialization. A static block should only contain simple and safe initialization logic. Throwing exceptions from static blocks is considered dangerous because it can bring down the application during startup. Next, what happens if an exception is thrown in both try and finally blocks? Here is the answer. If an exception is thrown in both the try block and the finally block, the exception from the finally block takes precedence. This means the original exception from the try block is completely lost unless it is explicitly handled or preserved. This behavior is one of the most dangerous traps in Java exception handling. Developers may unintentionally hide the real cause of a failure by throwing another exception in the finally block. For example, if an exception occurs during business logic in the try block and another exception occurs while closing resources in finally, only the latter is reported. Interviewers often ask this question to see if candidates understand why throwing exceptions in finally is discouraged. The correct practice is to avoid throwing new exceptions in finally blocks. Finally should focus only on cleanup, and any exceptions during cleanup should be handled carefully. A good interview answer highlights that losing the original exception makes debugging extremely difficult and should be avoided in production code. Next, what is the difference between checked and unchecked exceptions? Checked exceptions are exceptions that must be either caught or declared in the method signature. Unchecked exceptions do not require explicit handling. Checked exceptions represent recoverable conditions such as missing resources or external failures. Unchecked exceptions usually indicate programming errors such as invalid logic or incorrect assumptions. The most common interview trap is asking whether unchecked exceptions should be ignored. The correct answer is no. They should be handled when recovery is possible, even though the compiler does not force it. Another trap is assuming checked exceptions are always better. Overusing checked exceptions can clutter code and reduce readability. Interviewers also test whether candidates understand that unchecked exceptions can propagate freely and may cause application crashes if not handled properly. A strong answer explains that exception choice is a design decision. Checked exceptions are for recoverable situations, unchecked exceptions are for programming mistakes. Understanding this balance separates experienced developers from beginners. Next, how should exceptions be handled in multi-threaded Java applications? Exception handling in multi-threaded applications is more complex than in single-threaded programs. An exception thrown in one thread does not affect other threads directly. If an exception is not handled inside a thread, that thread terminates silently. This is a common interview trap. Many candidates assume exceptions propagate to the main thread. They do not. Each thread must handle its own exceptions or use a centralized mechanism to capture failures. In production systems, unhandled thread exceptions can cause partial failures that are hard to detect. Logging and monitoring become essential. Another key practice is ensuring shared resources remain consistent when exceptions occur. Locks must be released and state must be restored safely. A strong interview answer explains that multi-threaded exception handling requires careful design, clear responsibility, and strong observability to avoid silent failures. Explain the internal working of HashMap in Java. HashMap stores data in key-value pairs and internally uses an array of buckets. When you put an entry into a HashMap, the key's hash code is first calculated. This hash code is then transformed into an index that points to a specific bucket in the internal array. Each bucket can hold multiple entries. Initially, each bucket behaves like a linked structure where entries are connected in sequence. When a key-value pair is added, HashMap checks whether the bucket already contains entries. If the bucket is empty, the entry is stored directly. If not, HashMap compares keys to decide whether to replace an existing value or add a new entry. Retrieval works the same way. The key's hash code determines the bucket and then equals comparison is used to find the exact entry inside that bucket. Interviewers ask this question to test understanding of hashing, indexing, and collision handling. A strong answer explains that HashMap performance depends on good hashcode distribution. Poor hash codes cause too many entries in one bucket, degrading performance. This internal design allows HashMap to provide fast access in most real-world scenarios. Next question. What happens when two keys have the same hash code? When two keys have the same hash code, a hash collision occurs. In this case, both keys are mapped to the same bucket in the HashMap. HashMap does not rely only on the hash code. It also uses the equals method to distinguish between keys. When inserting the second key, HashMap checks existing entries in the bucket. If equals returns true, the value is replaced. If equals returns false, the new entry is added to the bucket. During retrieval, HashMap again calculates the hash code, goes to the same bucket, and then iterates through entries using equals to find the correct key. Interviewers often trap candidates by asking whether same hash code means same object. It does not. Hash codes can be equal while objects are different. A strong answer explains that proper implementation of both hash code and equals is critical. If equals is not implemented correctly, HashMap behavior becomes unpredictable. Understanding collision handling is essential for writing correct and performant Java applications. Next, what changes were introduced in HashMap in Java 8? Java 8 introduced an important improvement to HashMap to handle excessive collisions. Before Java 8, buckets used only linked structures. In worst-case scenarios, this caused performance to degrade significantly. In Java 8, when the number of entries in a bucket crosses a threshold, the bucket structure is transformed into a balanced tree. This change improves lookup performance from linear time to logarithmic time in heavily collided buckets. Interviewers often ask this question to check whether candidates understand performance evolution, not just syntax. This change made HashMap much more resilient to poor hash distributions and malicious inputs. A strong answer explains that Java 8 improved worst-case performance while keeping average performance fast. This shows that Java collections continuously evolve to handle real-world scalability and security challenges. Next, how does concurrent HashMap improve performance in a multi-threaded environment? Concurrent HashMap is designed specifically for high concurrency scenarios. Unlike HashMap, it allows multiple threads to read and write concurrently without blocking the entire structure. Instead of locking the whole map, concurrent HashMap uses fine-grained locking and non-blocking techniques. This allows multiple threads to operate on different parts of the map at the same time. Read operations are mostly lock-free, which significantly improves performance in read-heavy workloads. Interviewers ask this question to see whether candidates understand that thread safety alone is not enough. Performance under concurrency matters. Concurrent HashMap avoids common bottlenecks seen in synchronized maps. This makes it suitable for caching, shared state, and high-throughput systems. A strong answer explains that concurrent HashMap balances safety and scalability, making it ideal for modern multi-core applications. Next, what is the internal difference between HashMap and concurrent HashMap? HashMap is not thread-safe and does not provide any synchronization. Concurrent HashMap, on the other hand, is built for concurrent access. Its internal design allows multiple threads to read and update the map safely. HashMap uses a single internal structure without any concurrency control. If accessed by multiple threads without synchronization, it can lead to data corruption. Concurrent HashMap uses advanced concurrency techniques to reduce contention. It avoids locking the entire map, allowing higher throughput. Interviewers often check whether candidates understand why synchronized HashMap is not enough. Synchronization blocks all access, hurting scalability. A strong answer explains that concurrent HashMap is not just a thread-safe HashMap, but a carefully designed data structure optimized for concurrency. This distinction is crucial when designing high-performance, multi-threaded Java systems. Next question. Name the algorithms used by arrays.sort and collections.sort methods. Arrays.sort and collections.sort methods use different sorting strategies depending on the data type being sorted. For primitive arrays, arrays.sort method uses a highly optimized dual pivot quicksort. This algorithm is fast in practice, uses less memory, and performs very well for large primitive datasets. It is not stable, but stability is usually not required for primitives. For object arrays, arrays.sort method uses timsort, which is a hybrid sorting algorithm derived from merge sort and insertion sort. Timsort is stable and performs exceptionally well on partially sorted data. Collections.sort method internally converts the collection into an array and then delegates sorting to arrays.sort. This means it also uses timsort for object sorting. Interviewers often ask this question to see whether candidates know that Java uses different algorithms for primitives and objects. A strong answer explains that algorithm choice depends on stability requirements, memory usage, and real-world performance characteristics. This shows awareness of Java's internal optimizations rather than just API usage. Next question. When should a tree set be preferred over hash set? Tree set should be preferred over hash set when sorted, order or range-based operations are required. Hash set stores elements without any guaranteed order. It is optimized for fast insertion and lookup, but does not maintain sorting. Tree set, on the other hand, stores elements in a sorted structure. Elements are ordered either by their natural ordering or by a custom comparator. If your application needs operations like finding the smallest element, largest element, or retrieving a subset within a range, tree set is the correct choice. Interviewers often check whether candidates understand the performance trade-off. Hash set provides faster average performance, while tree set has slightly slower operations due to maintaining order. Tree set is also useful when predictable iteration order is required. Hash set does not guarantee any consistent iteration order. A strong answer explains that tree set trades speed for ordering and should be used only when ordering or range queries are necessary. Next question. Why is HashMap not thread safe? HashMap is not thread safe because it does not provide any synchronization for concurrent access. If multiple threads modify a HashMap at the same time, without proper synchronization, its internal structure can become corrupted. This can lead to data inconsistency, infinite loops, or lost updates. HashMap is designed for single-threaded or externally synchronized use cases. Adding built-in synchronization would slow down performance for the majority of use cases where concurrency is not required. Interviewers often ask this question to see whether candidates understand the difference between thread safety and performance. Using a synchronized wrapper around HashMap makes it thread safe but significantly reduces concurrency because it locks the entire map. Modern applications prefer specialized concurrent collections that are designed for multi-threaded access without heavy locking. A strong answer explains that HashMap's lack of thread safety is a deliberate design decision focused on speed and simplicity. Next, how does resizing work in HashMap? HashMap resizes when the number of entries exceed a certain threshold. This threshold is calculated using the current capacity and a load factor. When the map grows beyond this limit, resizing is triggered to maintain efficient access. During resizing, a new internal array with larger capacity is created. Existing entries are then redistributed into the new array based on their hash values. This process is expensive because all entries must be reprocessed. That is why frequent resizing can impact performance. Interviewers often test whether candidates understand why choosing an appropriate initial capacity matters. By setting an initial capacity close to the expected number of entries, developers can reduce the number of resizing operations. A strong answer explains that resizing is essential for maintaining performance but should be minimized through proper configuration and capacity planning. Next, what happens if a mutable object is used as a HashMap key? Using a mutable object as a HashMap key is dangerous and can break map behavior. HashMap relies on the key's hash code and equality to store and retrieve values. If a key's internal state changes after insertion, its hash code may change. When this happens, the entry may end up in the wrong bucket. As a result, retrieving the value using the same key may fail even though the entry exists in the map. Interviewers ask this question to test understanding of hashing contracts. Keys must be immutable or at least not modified while used in a map. This issue can lead to memory leaks, incorrect behavior, and very hard to debug problems. A strong answer explains that keys should be immutable and must have stable hash code and equals behavior throughout their lifetime in the map. This rule is fundamental for using hash-based collections safely and correctly.